My name is John Phillips. I'm going to be talking about something a little bit different. I'm going to be talking about evidence for rotating planar anisotropies in Sloan Digital Sky Survey satellites, or as is the actual title of my talk. Oops. Wait. Satellites on the plane. So just to give a bit of motivation for this, the evidence for these sort of planar anisotropies of satellites has existed for about 40 years around our own Milky Way. Here I'm showing a plot from Marcel Pawlowski's 2012 paper sort of demonstrating the alignment of the normals to the orbits of these Milky Way satellites. Recently we've seen potential evidence for planar alignments of satellites around Cen. So here these dotted lines represent the proposed planar alignments of satellites, but the gold standard as far as I'm concerned, and as far as I think pretty much anyone who studies planes of satellites is concerned, is M31. So here the red points demonstrate are 15 satellites that lie in tight planar alignment around M31. And in the bottom right, you can actually see of those 15 satellites, 13 of them have the same sort of sense of rotation around M31. So with seemingly strong evidence of this sort of phenomenon existing in the universe, the search is on to try and find evidence for this in large-scale surveys like Sloan. And about a year ago, a paper came out in Nature by Neil Ibata claiming to have found it. So on the right here, this is pairs of satellites, the cumulative co-rotating number of pairs over the counter-rotating number of pairs as a function of this opening angle alpha, which is defined in this cartoon here. So at small alpha, the pairs of satellites are very close to diametric opposition. And what they found is at small alpha, the ratio of co-rotating pairs is quite a bit higher with respect to counter-rotating pairs. And the proposed reason for that is these rotating planes of satellites that are being seen in edge-on configurations to us. So why should we care about these planes of satellites? Well, that raises questions about potentially we're seeing destruction of off-plane satellites or filamentary infall of these satellites being imprinted on their orbits. And in the bigger picture, this presents a bit of a challenge to lambda CDM. It doesn't come out easily in simulations, and it potentially could inform our models of evolution of satellite galaxies. So in short, these kinds of things, if they're real, could create trouble. And it would really behoove us to figure out if the evidence for their existence is substantive. So the experiment we want to do is to go into Sloan and look for pairs of satellite galaxies and examine these pairs for evidence of planar co-rotation. I'll quickly describe our selection criteria. So what we want to do is pick out hosts that are like M31. So they're bright and are reasonably isolated. And then our satellites we take to be brighter than R-band magnitude of -16. So after selection, we end up with about 400 hosts and almost 1,000 satellites. And so we want to look at these pairs of satellites for excess of co-rotation over counter-rotation, and we find it at small alpha. We find the same thing that the Ibata group did. Here we're seeing the counts of co-rotating pairs versus counter-rotating pairs as a function of alpha, and you can see co-rotation is in excess over counter-rotation at small alpha. But if we zoom out and look at the full dynamical range of alpha, we have a different picture. So this is the fraction of satellite pairs that are co-rotating as a function of alpha over the full 180-degree range of alpha. And you can see that there doesn't seem to be much structure there. And maybe my job is done. There doesn't seem to be any particular signal of co-rotation, but we're going to do a little bit more. We're going to examine this in the light of toy models of satellite dynamics and compare our toy models to the data. So this is just a cartoon of our model. We take a host at the center, at the origin, and then place several satellites in rotation about that host. And then we rotate the host and do a mock observation on it. And so when we do that, again, this is the data, and this is the mock observation of several thousand statistical samples, and we can see that it doesn't agree at all with the data, which is perhaps not surprising. But I'll draw your attention to one qualitative feature of the model function. So it carries weight. Oh, okay. It carries weight at intermediate alpha. So this is because in the model we have satellite galaxies that are not at diametric opposition, that are in fact at some other angle, and then the plane that they're in is not being viewed edge on. It's being viewed at non-zero inclination, which is something that the data doesn't have. So to try and bring our model more into agreement with the data, we add in a background isotropic model, which is just satellites being placed in random locations about the host and being given random velocity vectors. And as we increase the amount of isotropic background in the statistical sample, it comes into better and better agreement with the Sloan data. But again, this qualitative difference of weight at intermediate alpha still remains. So the question becomes, how can we adjust the model to try and get rid of the signal at intermediate alpha? There's two things we can do. We can either adjust our selection parameters such that we're cutting out all of the face-on disks so we only see edge-on disks, or we can fundamentally adjust our model so that we restrict our satellites to being at diametric opposition. So limit them to a narrow range of alpha. And we'll adjust those two possibilities separately here in the last couple minutes. So this is a plot of the Sloan data in host satellite velocity offset space versus projected distance from the satellite to the host. And what I'd like to do is draw your attention to the cyan points. These are the points that are at small alpha, so near diametric opposition. And the dashed line represents the median velocity offset for all those points. So if we assume that these satellites are rotating in a disk with a given velocity, v0, then we would expect, if we're looking at edge-on disks, to have that v0 be very close to our selection velocity, when in fact it is about 3 times higher than selection velocity. So we don't seem to be selecting in such a way that we would only find face on edge-on disks. We would expect to see some contamination from face-on disks. So that doesn't seem to be what's going on here. Now, the other option is, again, to constrain our model in such a way that satellites are required to be at small alpha. This is what we've taken to calling the dumbbell model. And we can see that actually does a good job of representing the data. It suppresses the signal at intermediate alpha while still maintaining the signal at low alpha, which was the motivation for looking for a model in the first place. Now, the problem with this model is its physicality, and that it doesn't seem to be physical. This represents what you'd have to do to make the model work, and it just doesn't seem to be something that makes sense physically. So we reject that possibility as well. So where does this leave us? Well, here again, the blue line is the Sloan data, and the black line is a perhaps suggestively chosen isotropic realization, or realization of the isotropic model. And you can see it has the same sort of bumps and wiggles. It has a higher co-rotation fraction at small alpha just purely by chance. And ultimately, we feel like that is what the data is. It's a representation of just a random selection in this sort of cosmic variance space. So I'll just leave up my conclusions. We find that planes as traced by bright satellites are not ubiquitous. We place an upper limit of maybe 10% of hosts can have planes like this. But we add the caveat that the satellites in our sample are brighter than anything seen in the M31 planes. So planes that are like the M31 may yet still be out there. And the hunt is still very much on for them. Okay, that's it.
All right, questions?
If it's only 10% on planes, then our galaxy in M31, to most well-studied examples, have nice planes. So is that odd?
It is, but again, the M31 plane, those are fainter satellites. So these are planes traced by brighter satellites that, if we applied our selection criteria to the M31 plane, we wouldn't see it. And same with the Milky Way.
So it's only small satellites?
Yeah.
On the planes. Okay, thank you.
Any other question?